Students, we are working on implicit differentiation, and this is the kind of differentiation you use when you have an equation that is not easily solved for the y. So I thought I would do a quick little vocabulary for you. Explicit form is when an equation is solved for y. So just a simple linear one, y equals 5x plus 2. But we could take that same equation and put it in implicit form, and that's when the equation is not solved for y, so like 5x minus y equals negative 2. And sometimes you'll find that there are equations that are actually difficult, or maybe it is impossible to get the y by itself. If you look at your two examples that are showing at the bottom of this screen, they're both written in implicit form right now. But number one, we could do some algebra and get that to y equals. We could subtract the x cubed and then do the cubed root. But problem two, even after factoring, we still wouldn't be able to get that to just a y equals. So that one's going to have to stay in implicit form, and therefore we'll do implicit differentiation. So I've given you some guidelines. One thing I would think that is important is that you use the d dx notation, because you're going to be doing the derivative with respect to x. And the chain rule is involved because anytime that we do a derivative of a y, we will have a term called dy dx. And that actually is going to be the variable that we'll be solving for. So I'll scroll up and we'll work on our first two examples at the bottom of your page. So problem number one is x to the third plus y to the third equals 8. And this asks us to do implicit differentiation. So what I like to do is to put a parentheses around the problem, and I'm going to actually white out the problem number right there if I can. And do the notation that I'm taking the derivative with respect to x of that entire equation. And so just to demonstrate what that is, that means that I'll be doing the derivative with respect to x of x to the third plus, and then I'll be doing the derivative with respect to x of y to the third, and then equals, and I'll be doing the derivative with respect to x of 8. And so anytime that you're doing the derivative of just an x term, you do your power rule and no other changes. So for x to the third, that would become 3x to the second. But in my next derivative, I'll be doing the derivative of a y term. So I'll still do the power rule, 3y squared. But because I'm doing the derivative of a y, but it's with respect to x, I have to do the derivative of the y with respect to x. That's like doing the derivative of the inside. It's a chain. And we write that as dy dx. So I'm doing the derivative of the y with respect to x. And then on the other side of the equal sign, I have my constant 8, and its derivative is 0. So there's your calculus line doing the derivative. And then your goal is to get the dy dx by itself. So you could subtract 3x squared from both sides. We'd have 3y squared dy dx equals negative 3x squared. And then we can divide both sides by 3y squared because our goal is to get dy dx equals. So dy dx equals negative 3x squared over 3y squared. And then we can simplify that. You can cancel out the 3's, and that would equal then, so dy dx equals negative x squared over y squared. And that would be your final answer for that. So the derivative, notice, has both an x and a y in the final answer. Okay, for your second problem, you have x to the third y to the third minus y equals x. So notice that there's just not an algebraic way to get the y by itself. And so we'll have to do the derivative with respect to x of both sides of that equation. Now, I'm going to show that again. So I'm doing the derivative with respect to x of x to the third, y to the third. And then I'll be doing the derivative, so minus, then the derivative with respect to x of the y term. And then after the equal sign, the derivative with respect to x of the x term. All right, so what I want you to notice about the first derivative here is that you have a product rule. So we'll have to do first d second. So first times the derivative of the y third. Well, that would be 3y squared, but because it's a y, we'll have to multiply by dy dx. So that's first d second plus second, and we're not doing a derivative, so we just list it, times the derivative of the first. So times the derivative of x to the third, which is 3x squared. And that's an x, so we don't have to have a dy dx. All right, then that takes care of that first part. Now we'll be doing this part next. So the derivative of y is a 1, but because it's a y, we'll have dy dx. And then we'll move on to after the equal sign, and we'll be doing the derivative of x with respect to x, and that is a 1. So now our job is to do the algebra so that we get dy dx by itself. So if you look in your list of instructions, you want to basically collect all the dy dx terms on the left and everything else on the right side of the equal sign. So we have a dy dx term here and here. We want to leave those on the left-hand side of the equal sign and subtract over the y to the third 3x squared. Now, I'm going to do a little bit of cleaning up, just rearranging things. So, for example, I'm going to write this as 3x to the third y squared dy dx minus 1 dy dx, and I kind of recommend keeping that 1. And then equals 1 minus, and I'm bringing that other term to the right-hand side, so I'm going to make it 3x to the second y to the third. All right, so now I have two terms that have dy dx in it. I'm going to factor out dy dx. That's my common factor. and it's also the variable that I'm trying to isolate. And that's going to give me 3x to the third, y to the second, minus 1. And then on the other side of the equal sign, just recopy. And finally, then I will be solving for dy dx by dividing on both sides by my parentheses. So dy dx equals, and then in my numerator, 1 minus 3x to the second, y to the third. And in my denominator, what was in the parentheses, 3x to the third, y to the second, minus 1. So notice that if you had to evaluate this by implicit differentiation, you would not just be able to use an x value, but you would need an ordered pair because you would have to substitute in for both x and y. But don't let the dy dx fool you. The dy dx is still a derivative, and so it's still a formula for finding the slope of a tangent line. All right, I'm going to clear the ink, and we'll work on problem 3, also at the bottom of this page. And hopefully you've had enough room to write. I just can't write that small with this pen. So your third problem, again, would be difficult to get the y by itself. Actually, I can't think of a way that we could do that. So we're going to do the derivative with respect to x of that entire equation. So now this time I'm going to skip the step. Hopefully you have seen it enough that you know I'm doing the derivative of each term. So I'm not going to show that step this time. I'm just going to do the derivative. So the derivative of sine of x is cosine of x. And then we're ready to move to the plus 2 cosine 2y. So plus, now my derivative of 2 cosine 2y would be 2, and it's the derivative of cosine, which is negative sine, and I keep my angle 2y, and then I have to multiply by the derivative of the angle, which is a 2, and it's a y, so I'll have to do dy dx. And then on the other side of the equal sign, the derivative of the constant 1, which would be 0. So again, my goal is to get dy dx by itself. I'm going to do a little bit of simplifying. So I have the cosine of x. I have a 2 times a negative times another 2. That'll be negative 4 times the sine of 2y, and then times dy dx. So that equals 0. I can subtract cosine x to the other side, leaving me with negative 4 times the sine of 2y dy dx. And that's going to equal, moving that cosine x over will be negative cosine of x. And then finally, my final answer, I can divide both sides by the negative 4 sine of 2y, and that will make my dy dx equal. Now, because I have the two negatives, I'm going to make it a positive. So cosine of x in the numerator, and in the denominator, 4 times the sine of 2y. So there's your introduction to implicit differentiation. And we do just have one more problem to do, but I think I am going to put it on a separate video since it's an application.